Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are beginning our study of Chapter 7, which is on equations of state for pure substances. Let's begin by reviewing the phase rule. If you'll recall, pi is the number of phases, n is the number of components, and R would be the number of independent reactions in our system. Gibbs' phase rule says that the degrees of freedom F is 2 minus pi plus n minus R. F, the degrees of freedom, is how many independent variables are required to uniquely identify the intensive state of a system. We're looking at this primarily at this phase for pure systems, so the number of components will be 1, and we are doing no reactions. Again, with a pure system, don't have a reaction. So n is 1, R is 0, therefore the degrees of freedom will be 3 minus the number of phases. In this chapter, we're looking at systems that are single phase, so therefore the number of phases 1, 3 minus 1 is 2. We will need to have 2 independent variables. We will be looking in the next chapter at multi-phase systems. The first equation of state that we all know and love is the ideal gas equation, or the ideal gas state. A substance behaves as an ideal gas whenever, first of all, the phase is a gas phase, right? A liquid will never be an ideal gas. A solid will never be an ideal gas. Being a gas is critical to being considered an ideal gas. Second, the ideal gas is based on molecules that are round and small, so they need to be totally spherical. The molecules also need to be far apart and have no attraction or repulsion to one another. Basically, every gas molecule behaves as a perfect little sphere, just all by itself, moving around in essentially empty space. The constant in the equation is called the universal gas constant, and it's designated R. R is, in one set of units, 8.3145 kilonewtons times meters per kilomole Kelvin. If we want this in kilograms, R in kilonewtons times meters per kilogram Kelvin, we'll take the universal gas constant R and divide it by the molecular weight. We use this in the ideal gas equation of state, PV equals nRT, or PV equals mRT if we are using the R on a mass basis. If we are looking at specific volume, not total volume, PV equals RT, and when V is going to be molar volume, volume per unit mole, R is the universal value. If we want volume per unit mass, then we need to be using the universal gas constant divided by the molecular weight. In all cases, pressure and temperature have to be absolute to use this equation. And the units for the volume will depend on what our choice is for R. One of the nice things to do with this is to consider a closed system. In that case, pressure times total volume over temperature will be a constant because mass is a constant and the gas constant is a constant. So therefore, P1 V1 over T1 would be equal to P times V over T at state 2. And these are useful equations, and we've experienced using all of these. But now we want to look at some other equations of state, and the first category of these will be the cubic equations of state. A cubic polynomial is the simplest mathematical form that can represent both the liquid and the vapor phase. There's also going to be a virial equation. It's a little bit more of a challenge to use simply because it's based on statistical mechanics and the models are not always available for all substances. The cubic equation is better than the ideal gas law because it doesn't, the cubic equations allow for molecules to be more realistic, right? They don't have to be super small. They don't have to be perfectly spherical. They can have attraction and repulsion forces between molecules. So this is what our goal is, to improve upon the ideal gas law in a way that is reasonably representative of reality. Now, the first one to do this was van der Waals, and in 1873, he was a Dutch scientist, and he developed this equation. P is equal to RT over V minus B minus A over V squared. Pressure, temperature, and volume, these are molar volumes, are the same as what we've seen before, but we've got some changes. We've introduced two new constants, A and B, which are values that depend on the substance under consideration. And if you had B equal to 0, P equals RT over V, that first portion there would indicate that you have the ideal gas law. So what we've done with our first term is we've expanded for a volume that's not infinitesimal, so V minus B. And the A over V squared term is accounting for the fact that molecules actually do interact with one another. Now this equation can be rearranged algebraically by multiplying through both sides by the denominators of these fractions, and you get PV squared times V minus B equals RTV squared minus A times V minus B. And what you should recognize is that this is a cubic third order polynomial in V. Now the van der Waals equation actually works remarkably well for being the first in this whole family of improvements on the ideal gas law, but we can make it even better. So things that are good about it is the being third order in volume. That actually really does do a good job of describing what happens in nature that includes both the liquid and the gas considerations. So we'd like to keep that cubic piece there. We'd also like to keep the attraction term, the A over V squared, something about that. And we'd like to keep the repulsion term, the RT over V minus B, the fact that they actually have size, okay? But the improvements that were made, well, first of all, that constant A over something like V squared, A really shouldn't be constant, okay? That will vary with temperature. And then also the denominator in that attraction term, A over V squared, that's more complex than maybe just a simple V squared. And so the denominator of that term actually turns out should relate to the parameter B, which is essentially relates to the maximum compression you can do on a molecule. Now, I do want to remind you that everything at this point in the book is all on a volume per unit mole basis, so molar volume. And in the book, they are underlining those. Thanks to the equation editor tools, that's not going to happen in our notes, but these are all per unit mole. They can be adapted to per unit mass, but specifically these are done for per unit mole. So the first of these, well, there was a REDLICH-KWONG equation developed in 1949, and that wasn't too bad. It was an improvement. In 1972, SOAVE improved the REDLICH-KWONG equation, and we ended up with the SOAVE REDLICH-KWONG or SRK equation of state. This one is really very popular. In this, P is equal to RT over V minus B. We see that same first term, minus A, which is a function of temperature, over V times V plus B. If we rewrite this in terms of compressibility, so P times V over RT is equal to Z. Multiplying this through, we get Z is V over V minus B minus A over RT times 1 over V plus B. And so either form here is the SOAVE-REDLICH-KWONG equation. And A and B, again, are going to vary with our substance. We also have the PENG-ROBINSON equation of state, which is 1976. It has minor advantages and disadvantages over the SOAVE-REDLICH-KWONG. Both of them work fairly well for most substances. In this one, P is equal to RT over V minus B minus A, which is a function of temperature, over, and the denominator here is different, V times V plus B plus V times V minus B. Or in terms of compressibility, V over V minus B minus AV over RT times 1 over V plus B plus B, V minus B. So these are our key cubic equations of state. We have the van der Waals, which is historically significant and easier to work with. Does an adequate job, but not great. And then the two of these that have had the longest lasting staying power are the SRK and the PENG-ROBINSON equations of state. In our next video lesson, we're going to look at how we can use these. Thank you very much for your time.